All right. Hopefully those 4 questions were not a huge challenge for you. What I would like to do right now is take a look at a couple of homework questions that were missed by many people. So one of those was actually 9.3 number 2, homework 9.3 number 2, the very first problem. A lot of you tried to make this problem simpler than it is. And you were using as your example I didn't remember what it was. A problem in our notes that had, we were taking balls out of, am I making this up?
Is it the one where you pick them out of like one?
Yeah, we did that problem,
Yeah.
right? Yeah. So, but the difference was, in that problem, both containers had the same number of balls in it.
So it gets
Okay.
like
Yeah, so what happens in this homework problem though is that we've got 2 jars. We have jar 1 and jar 2. But jar 1 has 6 chocolate chip and 8 sugar. So jar 1 has how many cookies altogether? 14. So this is 6/14ths, and this is 8/14ths.
Yeah.
All right? And then jar 2 has 2 chocolate chips and 5 sugars, which makes 7. So this is 2 7ths, and then this is 5 7ths. So when Declan walks into the room, he has a 50-50 shot of picking either jar. But the probability of getting a certain cookie out of a certain jar, you can't look at it in total, because the total number is not the same. Remember, when you do probability, it's over the total. So, what did you want? What is the probability? It's a sugar cookie. So a sugar cookie is here or here. So that should be 1/2 times 8/14ths plus 1/2 times 5 7ths. So 4/14ths and 5/14ths. The answer to that question is 9/14ths. And what some of you did was just add up all the cookies right from the beginning, kind of ignoring the fact that they were in 2 different jars. Okay? Then, what's the probability that if it's a chocolate chip cookie, it is from the blue jar? Did I read right there on your paper? Oh, it did. That if he chooses a chocolate chip cookie, it came from the blue jar. So you guys, listen, we're gonna have a test over this, right? So we gotta just kind of lock in. So what's the probability that he gets a chocolate chip cookie given that it's from the blue jar? Okay, so given, okay, he gets a chocolate chip cookie from the blue jar. All right, so what does that look like?
Maybe you can just focus on one side.
Well, it's this is our formula for that kind of
Yeah.
situation, right? So what's the total probability of getting a cookie from the blue jar? The cookie from the blue jar, well, I numbered them, what did I have? They should have been colored. The blue one, this is the blue one. This is blue. And this is green. Okay, So what's the probability I get a cookie from the blue jar? That would be my denominator.
50%.
No, not 50%.
Or that you get.
This is the whole blue jar thing, right? This is the blue jar. So that probability is 6/14 times 1/2. And this one is 1/2 times 8/14. Oh, that does work out to be 1/2, doesn't it?
Yeah.
All right, so that's 1/2. And then I need a chocolate chip cookie from the blue jar. A chocolate chip cookie from the blue jar. That would be this term right here, which is 3/14. So I took blue and chocolate chip, and then all of the blues. So that is 6/14, or results. Okay, so some of us missed that one, now we got it. Okay, we're good. All right, anything else on any of the papers I turned back? Your quizzes or homeworks? We just have a lot of people miss that one.
Can we do number 2 on that homework?
Number 2, in a class of 34, 7, okay. So this sounds like a Venn diagram, doesn't it? Wait. I'm getting it. All right, so I have A's, B's, and C's. 7 get all 3. 5 get all A's. 2 get all B's. 4 get all C's. So we need to do our thing where we call this A, B, and C and set up our equations. Did you do that right?
Mm-hmm.
All right, what did you get? So what was this here, the overlap of the A and the B?
X, Y, Z. 5.
That was 5?
Yeah.
Yeah, okay, 5. And then this was,
8.
that was B and C. I had 1 here, and then this one was 8. Is that what yours looks like? Okay. So this is, I made a little note, it's a little confusing, so I get credit for a couple of different answers. What is the probability that he gets only A's and B's? Only A's and B's. So one kind of logical thing, how many kids are in the class? 34. So one kind of logical thing is to look right here, because aren't these the kids that get A's and B's? So that answer would be 5 over 34. That is kind of the, like, logical answer. But some people read it differently.
It kind of seems like it was.
And yeah, so that could be a little confusing, and say, you might think, well, wait, this kid gets all A's and B's too, but he just happens to get all A's. So I gave credit if you can make like these sections too. You can't have anything in the C range though. Right? Okay, Blake, you all right with that?
Yeah, I was gonna ask you about number 4 on the quiz.
That we just took?
No, on
The other quiz?
9192.
I missed you already.
I was just confused, like, what else I was supposed to do. I did 15 factorial.
Oh, wait, somebody help him out. I don't need to help him out with that, you know. He
Yeah.
counted up the letters and got 15 factorial. Well, there's another piece to it, isn't there? We have repeating letters.
Oh,
So we have to divide this by whatever is repeating.
2 factorial.
So we got a couple of S's,
do it.
a couple of I's,
I forgot.
2 I's, 2 A's, All right, who else?
Oh, this is another problem as well. So I did that, and then I got 3.179.
Yeah.
Times 10 to the 9. I just like
Okay.
I
First of all, your answer, 8.1, doesn't even make sense.
When I tell you just
Because if you say, how many ways can I arrange these letters, can we get a decimal? At the end of that number that you copied down was an E. And what does it mean when there's an E? It's the same as that. So you have to look all the way across.
It's the fifth number of the 23rd row, so
All right, anybody else before we get back to our notes? All right, let's get them out. We were kind of in the middle of something yesterday. Our exam day, not next week, but the next week, we are the lunch period for the exam day, and all seniors eat first lunch that day. So if you're taking the exam, coming to class, you eat lunch first, and then you take the exam. They'll publish the times and all that.
What day is it on?
May 12th, Tuesday. Your first day exams, you have 1, 2, 3, 4 that day. Okay. All right, so here are the directions. Tell what type it is, give an explicit formula, and give a recursive formula. Now, if you are still focused, this is all written down in problem above. If you were zoned out, you better pay close attention because this is the last example we have of this problem. This is 1B. 1B in 9.4. 1B. All right, we are going to tell what type of sequence we have. What are our choices? Geometric or arithmetic? And what's the difference between them? Right?
One's addition, subtraction, the other's.
And arithmetic, we add or subtract. Geometric, we multiply or divide. And I gave you the formulas for those two. This is your arithmetic formula. This is your geometric formula. I encourage you to write these down so I don't have to keep writing them down. You will never have to memorize them, at least not in this class. So just write them down somewhere so you have them to reference. Now, the question says, what kind is it? Well, what do you think? Look at those terms. What seems to be happening? Geometric. It looks like we are multiplying by -1/2. We call this ratio. Multiplying by -1/2. If we have a geometric sequence, then this will be our explicit formula. These are your explicit formulas right here. So we're going to plug in our first term. Remember, this means first term. That's ratio. So I plug in -2, and then -1/2 to the n minus first, and that's it. We talked about this earlier in the year with our exponential functions. These two numbers may be written right next to each other, but they cannot be combined because that one has an exponent. So they stay separate. Back when we did it before, we called it a times b to the x, and I told you never, ever, ever multiply a and b. You can't. So this is it. You're done. That is your explicit formula. Now, the recursive formula is the one that you answer by saying to yourself, what is the next term going to be? If I kept going, what would go right here? What? -1/8. Now tell me how you got that.
Because the pattern.
You took that guy, right? You took some term, some generic term, and you multiplied it by -1/2. And that gave you the next term in the list. So in our example, you took the fourth term, You multiplied it by -1/2 and you got the 5th term. Now, that is your recursive formula. Does anybody remember the extra little piece? I added it right at the end of the period. Did anybody think to write that down?
You have to do what you start with.
You have to write down what you started with. So my very first term is -2. And I hope that makes sense to you, because this formula says, take a term and multiply it by -1/2. Okay, great, but don't I have to have a term to get started with? So here it is, there's my first term. And then I'll multiply it by -1/2 and I'll get my second term, and so on and so on. Perfect. Did we talk about the Fibonacci sequence?
No.
All right, let me put it up here because, well, let's do C first. Let's do C first. And then we'll talk about the Fibonacci sequence. Now, this one says, write an explicit formula only. This one is hard. You really have to think. Is it arithmetic? Am I adding the same thing that I'm telling you, sir? Is there a pattern?
There's definitely.
Yes, but it's not the same thing. So to be arithmetic, you have to add the same thing. Since it's not arithmetic, I will not be using that formula. Is it geometric? Am I multiplying by the same thing? Nope. No, it's not Fibonacci either. So now I'm on my own to write a formula. This is hard. Okay, this is tricky. It's actually an inherited characteristic. Some people are really good at it. You have a chromosome or something for it. Other people just don't get it at all. So, anybody see a pattern that's going on? I didn't write my sequence down. Anybody see anything special about these numbers?
Every time you add something, you add 2 to how much you add it to.
Okay, so Michael has observed the pattern. He says I added 3, then I added 5, then I added 7, and so on. And that would be, that's wonderful. That would help me keep going, right? But remember, your job is to write a formula for that. That's what we're doing. What'd you say?
Second number minus the first number, like 15 minus 8.
Okay, again, we gotta write a formula for that. An explicit formula for that, which means something that looks like this. Add 1 to all of those numbers. What happens if you add 1 to all of them?
It can be, square rooted.
You get the perfect squares. So your formula is n squared minus 1. If you want a sub 1, that's 1 squared minus 1. Is that true? And then a sub, let's say 5, should be 5 squared minus 1. Is that true? So this is your formula. I'm not gonna give you anything like that on a test, because it is hard, but there's an example of how we have to handle a sequence that is not arithmetic or geometric. Oh, Fibonacci, the most famous sequence in the whole wide world, and that's why we have to talk about it, because it is so famous. Well, Leonardo Fibonacci was his name. This is the Fibonacci sequence, right here. So when somebody mentions Fibonacci, you will know what they're talking about. Can you see the pattern here?
Yeah, you add the number from before.
Exactly, so 2 and 3 makes 5, 3 and 5 makes 8, and so on. So the term that comes after 21 will be 34,
Yeah.
and then 55, and so on. In recursive terms, Fibonacci says, if you take some term and add the next one, you will get the next one. Now, for some reason, we get all confused when we see subscripts. This means some term, like the 5th term. If you take 1, 2, 3, 4, 5, if you take the 5th term and add the 6th term, you will get the 7th term. Isn't that exactly what you just told me?
5 plus.
So 2 consecutive terms, the number that comes after n is n plus 1. So you make 2 consecutive terms, and we add those, and then we get the next term after that.
Same as like 1,
Really?
2, 5.
Well, this would not generate 1, 2, 3.
You add
That doesn't even make like,
2
we put numbers
You get
in the
3,
show.
but then the number that would come after that would be 5.
Can we put some numbers in the show?
What? Because I have 2 numbers in here added, I am going to need 2 starting numbers, so 1 and 1 are my starting numbers. The Fibonacci pattern is so famous because it's everywhere. If you're out traipsing around the woods and you pick up a pine cone, if there are 21 kernels, you know those little things, 21 kernels in one layer of the pine cone, the one above it will have 13, the one above it will have 8, and so on, all the way to the top, unless it's been damaged by something. It's in bee honeycombs. You know what bee honeycombs look like, where they put all their honey? That pattern is is there. It's everywhere in nature. Google it. It's fascinating. Leonardo Fibonacci, actually discovered it within a rabbit population. And you can read about that too if you want. But we don't have to do that. So, anyway, that's Fibonacci. Just for your information. All right, let's do some more problems.
FYI.
Yep, FYI. Here is an explicit formula. Somebody has made this up. Here's another one. These are explicit formulas. Remember, A sub n, explicit formula. It says, find the first 3 terms. Now, we need to get used to the notation. A sub 1 means first term. A sub 2 means second term, and so on. If you have an explicit formula, it's as easy as plugging in. A sub 1 would be 1 plus 1 over 1. So that would be 2. A sub 2 would be 2 plus 1 over 2, which is 3 halves. A sub 3 would be 4 thirds. And we're not doing any more, but we're skipping to 50. A sub 50 would be 51 over 50. That's it, that's all there is to it. You're practicing with your sequence notation. A sub, that's it.
You're the man.
All right, what about this one? What's the first term of this one? 4 over 3. Second term is? So 1, 4 over 4. A sub 3, 4 fifths. And then skip to A sub 50, which we always reduce, so that would be 1/13. Easy. Nothing to it. Huh?
That's A sub 3.
3. New vocabulary. Is the sequence divergent or convergent? If it is convergent, give the limit. What does divergent mean? Kind of shooting out, right? No limitation on it. Yeah, yeah. So your question is, and we're gonna talk about easy ways, there's quite a few of these problems. We're gonna talk about easy ways to tell, but just right now, knowing really not too much about it, what do you think about A, the sequence of squares? 1, 4, 9, 16. So do you think it's limited in any way, or do you think it's just gonna go? What do you think? Divergent. So number one, A is divergent. It is not limited in any way. And again, we're gonna spend more time talking about this, but let's just kind of intuitively figure a couple of these out. The next sequence, 1/2, 1/4, 1/8, 1/16, 1/32. What's going on with those numbers? They're getting smaller and smaller. Now, are they gonna get smaller and smaller and smaller and smaller, like forever, like to negative infinity smaller? They're just gonna keep on going? Or are they limited in any way?
Limited
What are they limited by?
fraction,
Well, because it's that fraction, they're limited.
so 0.
The 0, absolutely, Jimmy. So that one is convergent, and its limit is 0. I want everybody to just think about that for a minute. Are the terms of the sequence getting smaller?
Yeah.
Yes. Are they, if I'm 0, the terms are getting smaller. So here's 1/2, 1/4, 1/8, 1/16. They're marching down the number line, getting closer to me. I'm 0. Are they ever gonna pass me and come over here? No, so I am acting like a limit. I'm like a wall that they can't go past. They're gonna keep getting closer to me, but they're never gonna get past me. That's exactly right. So that one is convergent and has a limit at 0. Jimmy?
Actually, cause it's a fraction, if it was like 5/4, would the limit be 1?
No, if it were 5/4, it would be divergent. Because if you keep multiplying by 5/4, doesn't it just keep getting bigger? So Jimmy, you just hit on something really, really important. When we have a fraction to a power, so we have like, our first example was 1/2, your example was 5/4. When you have a fraction to a power, if that fraction is less than 1, the limit will always be 0. Because if you keep multiplying by a number less than 1, so in other words, this could be 1/7, it could be 4/7, it could be anything less than 1, it keeps getting smaller. And so that limit will always be 0. Always. On the other hand, if your fraction is bigger than 1, I'm talking about the thing you're taking to the power. If your fraction is bigger than 1, then this will just keep getting bigger and bigger and bigger, which means this is divergent. Divergent means no limit. So every problem that's structured like this, that's gonna be your key. So look with me quickly at H. Problem H. What is the limit of H? 0. You don't need to think twice. All your beaded little eyes do is look at that 2/3. That's 0. What about I? Divergent. Right, don't say no. Say either no limit or divergent. How about J? Divergent. Here's the deal, kids. The whole shebang depends on the fraction. I don't care what the exponent is, okay? So that's divergent. J is divergent. What about K? Zero, because 0.36 is less than one. Always divergent
No
or
other
zero.
limits.
No, what, no other limits for problems that are structured like this. Okay? So what about L? Divergent, divergent. All right, so H through L are Jimmy's theory, we'll call it over here. All right? The idea is, if you are a fraction or decimal to a power, your limit is gonna be 0 or no limit, depending on the size of the thing being raised to the power. Okay? Now, there's a whole bunch of other problems that don't work like that. What about C? C is structured differently. All right? But you know how to do this one too. I want you to think back, not that long ago.
It looks like if we were doing a vertical and
Oh my gosh, we are on fire today.
So limits are gonna be the asymptote.
We saw problems like this. This is letter C, but I've changed the letters so that it looks the way it used to look. And Michael says, we had asymptotes in that picture. We did. We had two kinds of asymptotes. What kind of asymptotes did we have? Vertical and horizontal. Your horizontal asymptote is the limit. And if you think about that, it makes sense, because when you have a horizontal asymptote, see what your curve is doing? Getting closer to it. So, who remembers how to find a horizontal asymptote? What?
3x over x.
Exactly, you box it in. So what is the limit of problem number C? 3. 3n over n, you box it in. What is the limit of problem D? -2. Why is the limit of problem D -2? Because we have -2n over 1n. Box them in, guys. Box in your n's. What do you think the limit of E is? 4 over 5, 4/5. 4/5.
It's the highest.
It's the highest power. When we box them in, it's the highest power. So the answer to E is 4/5. What about F? 0. Why is F 0? Because we've got no n squareds over 1n squared, and that is 0. What about G?
No solution.
No limit, because we have 8n squared over 0n squared. Remember that? When you've got n's over n's, you've got to box in the
As we pause
highest
for
power.
prayer, a quick reminder to join Father Johnny at 11:50 for mass if you would like to. We are down to a 10 more masses countdown left this school year with Father Johnny, so if you're able to go and grab a friend, join Father Johnny at 11:50. I know we'd love to see you. Also, Father Jeff will be available for confessions at the FLC during lunch period. Now let's watch tonight, God's blessing.